So there's lots of options for open source data formats for vector geospatial data. So the goal of this video is to just provide a brief introduction to some of those methods, their structure, and then like some pros and cons. All right, to start off with, I have a couple layers loaded in here. So this is the U.S. state boundaries and then major cities across the U.S. So one's a point layer and the other one is a polygon layer. And I actually got these from this folder here. So they're inside of an Esri file geodatabase right now. So they're stored as feature classes. So that's an example of a proprietary format. So what if we wanted to take this data and store it in a different format that would be open source or non-proprietary? So here in QGIS to do that, I'll start with the state layer. If we go to export, say feature as, there's tons of options here for different file formats. And we're not going to load all of these. I'm just going to look at some of the more common ones. So if you're a GIS person and you don't use QGIS, it's worth having on your machine just for the data export transformation options. Okay, so first thing I'm going to do is save this as an Esri shapefile. And I'm going to put it inside of this data formats folder here. So we'll call this states shape.shape. And we don't really need to change anything. It's currently in an outburst projection. That's fine. The encoding's fine. It should automatically figure out that it's polygon, but we'll just specifically tell it that. And we'll hit OK. Okay, so now we have a copy of that data layer. So if I go into the folder where I stored it, you can see that it's now copied as a shapefile. A shapefile is an example of a georelational data model, which means that the geometry and the attributes are actually stored in separate files. So for example, in a shapefile, the attribute information is inside of this .dbf file, whereas the geometric information is in this .shapefile, and then there's some ancillary files here like .shx is an index file to speed up loading and coring and drawing and whatnot. The .proj is the projection information, so I'm just going to open that up with Notepad here, and you can see this is a shapefile specific projection information standard, right? So you can see all the projection information, the name, the GEOI that's used, the datum, it's NAD83, the projection type, the easting and northings, the parallels, so on and so forth. Okay, so shapefiles are still probably the most used or one of the most used vector data types, but there are some issues and limitations. For example, there's limits on the file size and the number of features that you can have. One issue that I find specifically annoying is field names. So if I open up this attribute table, I'm just going to try to create a new field here. So if I start typing, it's eventually going to cut me off. And that's because you can only have a 10-character field name, which can be kind of annoying, especially if you have a lot of fields you want to differentiate. Okay, so even though shapefiles are commonly used, there's still some issues with them. So we'll look at some other options now. Note that shapefiles were originally generated by Esri, but they're considered non-proprietary now. Okay, so next option we're going to look at is Geojson. So do save file as. We're going to change this to Geojson, and let's see, give it a file name here. So we'll do cities geojson.geojson. Okay, and then we'll tell it it's specifically points, and I don't think we need to do anything else. I'm going to lower the coordinate precision a little, just so the file's smaller. It's easier and it'll be easier to look at if we look at the structure. Okay, that said it added it, but it didn't seem like it worked. There might be a projection issue with this layer. Let's see. Let's look at the source information here. It seems like it's projected okay. I'm not really sure why that didn't work. Let's do a zoom to layer and see if it actually drew anywhere. It's just not drawing it. Let's open up the attribute table. They're all there. I'm not sure why it's not drawing it. Let's look at the structure of that. So I'm going to again go back into this folder where I'm storing all these outputs. So data formats, that's the file there. Note it's now a single file. So this is like an object-based model as opposed to a georelational model. I'm going to open this up with WordPad again. Oh, it's not going to let me because it's in use. Let me remove it. And we'll go in and open it up. Open with WordPad. There we go. So this is the structure of that data, which looks kind of complicated. The key thing to know about this is that it's storing it in a structure known as JavaScript object notation. So if you know anything about like web programming, JavaScript is the dominant client-side web programming language. So JavaScript object notation is a way to store data that allows JavaScript to read and write it. So it's very useful in like a web environment for things like, you know, web apping and web apps and whatnot. Geojson just extends JSON to include the geographic information. So like the geographic coordinates and like the projection information and whatnot. So you can see all these like square brackets and curly brackets. Basically, a JavaScript object is a set of name-value pairs, so name, value, and you can string all those together inside of curly brackets to define an object. And then these square brackets can be used for, I guess they're lists. That might be Python. I think list is the right word. So it's basically a bunch of data structures defined by JavaScript, so it's readable by JavaScript. So if you're going to use data in a web environment, you're probably going to run into using GeoJSON occasionally. Okay, so next let's look at a KML file. So let's just do the states. We'll do export, save feature as, and we want to save it now to KML, which stands for Keyhole Markup Language. And we'll put that in this same folder. So we'll do KML, or states KML.KML. Note that a KMZ is this a compressed version of a KML, so you might see that extension sometimes. Okay, do we need to change anything? This should be fine. So let's hit OK there. It should have generated it, and let's go into the folder. And there we go. See, so it's got this little icon, which is the Google Earth Pro icon. So what I'm going to do is add, I'm going to do open with Google Earth, and let's see what it looks like. I think I had some layers loaded into here already, so it might take a second to load in or draw. Why that's in the process of drawing, let's just look at the structure real quick. So I'm going to do an open with WordPad here, and you can see the structure. So this is a markup language. So if you are familiar with things like HTML, hypertext markup language, which is used on the web, or extensible markup language, or XML, which is used on the web and also for things like metadata, it's effectively a bunch of information that's stored between tags, and those tags are how the computer understands how to interpret it. So for example, with HTML, if you're looking at building a web page, if it's in a p tag, it interprets that as a paragraph. If it's an h1, it's a header 1. If it's an image, it'll plot an image or whatever. So this is kind of the same thing. So you have a bunch of tags with information embedded in them. So this format was originally created for use in Google Earth by the people that generated Google Earth, which was Keyhole, which was eventually acquired by Google. All right, let's see here. So these are kind of hard to see because they're pretty much the same boundaries that are on the map already. Let's get rid of borders and labels. There we go. So all those red boundaries there, that's the KML file that we just created. Okay, so I don't use those a lot, but they can be useful, especially if you just want to like share some data with people, because Google Earth is easy to install and use, and it's easy to open KML files inside of it. All right, so next I want to look at some SQLite based methods. So I'm going to open up my web browser here real quick and go to this SQLite homepage. So SQLite is it's kind of similar to a file geodatabase, like you use in the Esri environment. So it's a database that's stored in a file folder type structure. So there's some positive attributes to SQLite. First off, it doesn't make use of like the client server architecture like a standard database management system. So you can install it on like client computers. You can even install it on mobile devices for like use in like mobile phone apps and whatnot. So it's fast. This thing, as the site says here, self-contained, really reliable. It's lots of features. You can query it using SQL. So basically, I want you to think of an SQLite as like a free, non-proprietary alternative to the file geodatabase. Okay, so if you want to store your data inside of an SQLite database, then there's two broad options. So the first option is SQLite, which can only store vector data currently, and then the other option is a GeoPackage, which can store both vector and raster data. So I'm going to specifically look at GeoPackages because they're a little more robust, but SpatialLite, the SpatialLite option is similar, but just for vector data. Okay, so what I'm going to do, I guess, to start off with is we're going to take this, we'll just start with the original states layer, and we're going to do a save as, and we're going to export that to a GeoPackage. We're going to create a file here, so this is actually not for the file itself, but for the database file. So you're actually creating a new database now. So we'll call this example, let's see, GeoPack.GPKG. So that's the extension there for a GeoPackage, which again is just uses SQLite. We'll do save, and then we want to name the file, the actual table or file we're going to store inside of the database. So this is like saving a feature class. So we're going to call this just states GP for GeoPackage. And then there's the projection info. We'll tell it specifically that we want it to be a polygon. Note that the geometry options that are available are going to be different depending on what type of layer you're writing into. So for things like GeoPackages, or SpatialLite, and even things like PostGIS, PostgreSQL, you're going to have like points, line strings, polygons. You can also have multi-point, multi-line, multi-polygon. No geometry effectively just means just the table with no geometric information. And the geometry collection can actually store multiple different types of geometry. So you can have one file where different records have different geometries. So one record could be a polygon, the next could be a point, the next could be a line, which isn't generally an option for an individual feature class in a file geodatabase or a file or a shapefile. It'll have to be the same geometry. So this is polygon, so we're going to stick with that. And I don't think we really need to change anything else, so we'll do OK. And now we have a third copy of this state layer. All right, so let's look at the structure of this. And to do that, I'm just going to open up this database manager, and we'll do GeoPackages here. We want to do new connection, and I'm going to create a connection to this database. Oh, this should be this one. Yep. Okay, and it's got the states layer in there. And we'll go into SQL here, and I'm just going to create a quick query. We'll do select asterisk, which means all the columns from, and then we'll do states underscore GP, and then end it with a semicolon. And if I execute that, you can see here that this is the structure of that data. So there's all your attributes from the states. And this column here that says geom, that's actually the geometric information. So this is an example of an object-based model where the spatial information and the tabulated or aspatial information is all stored in one file. If you want a more readable version of the geometry, I'm going to do st as text, and we'll do, I guess this is states gp dot geom, and then we'll call it as geotext. So this will create a new field. And actually, let's put it at the beginning just so it's easier to find. So I'm gonna get rid of this, do a cut, and then we'll do a paste there, and then we also want everything else. I think that'll do it. Let's execute it and see. Okay, so now we have this new field on the front end here, and that's all the geometry information. So this is well-known text, and it's all the coordinates that basically make up or define the state extents. Okay, so in my opinion, GeoPackages and SQ or SQLite structures which make use of SQLite are going to be a big deal in the future. I think we're going to see a lot more use of GeoPackages. So again, file geodatabases have now become like kind of the standard in the Esri environment, and GeoPackages offer a open source equivalent that has a lot of the same functionality. Okay, so just to finish up, I wanted to mention a few other resources here. So I'm going to open up this web browser and just point out a few websites. So there are a couple libraries that pretty much all open source geospatial software makes use of. So one of those is GDAL, which stands for, is it geographic or geospatial? I think it's Geospatial Data Abstraction Library. So effectively, this creates an abstract model where you can take some data in another format, like a shapefile, convert it into the abstract model, and then back into a different file format. So this allows you to do a bunch of conversions. And you can see that there's support for tons of different types of files. So you can see different raster file formats there. And then down here at the bottom, there's vector formats. So we have our shape files listed here. There's a GeoPackage. So this is important because it allows you to do your transformations of data types based on a common or standard abstract data model for raster and vector data. So pretty much all open geospatial software, and even some of the commercial software is making use of GDAL. Another package or tool that's working in the background is Proj, or what used to be known as Proj 4. And you can think about this as a library for working with and manipulating spatial reference information. So it maintains like a list of all the different spatial reference information, and then it can support transformations between them. All right. And then there's also some consortiums that kind of maintain all this stuff. So for one example is the Open Geospatial Consortium, and they deal with or maintain a bunch of open data standards. So you can see some of the ones we mentioned here. So things like KML files, these ones that start with W, WFS, WMS, WMTS. Those are open standards for like the internet-based services, so things like raster tile layers, feature services, map services. And then we also have the Open Source Geospatial Foundation, which maintains some tools. For example, things such as QGIS, GRASS, Orpheo Toolbox, which is a remote sensing toolbox, Geos, GDAL's there. So these organizations basically maintain this stuff, which is important. Okay, so to wrap up, I just wanted to provide a brief introduction of how we can access geospatial data in some of the open data science environments. Specifically, we're going to look at Python, and then we're going to look at R. Okay, so I've opened up a Jupyter notebook here inside of an Anaconda environment that has access to a bunch of libraries that allow you to work with data and spatial data. So what I'm going to do here is specifically show you how to read in a vector layer. So here I'm reading in our libraries that we need. So just to point some of these out, NumPy is used to work with data arrays and do math, basically work with numbers in Python. Pandas allows you to read in data frames, so you can store data in a structure that's similar to like a table in a spreadsheet, or like a CSV file, so basically a data table. And then we have Matplotlib, which allows you to make plots. And then these packages relate to spatial data. What we're specifically going to look at is GeoPandas, which is a geospatial extension for pandas. So I'm going to run this so we have access to our packages. You can see it running up there at the top. GeoPandas not found. Oh, I may have been in the wrong environment. Let me close this out real quick. Let me go back to my Anaconda here. And oh, sorry, I was in the wrong environment. So that environment I was in didn't have access to GeoPandas, so I had to switch to a different one that does. And we'll relaunch our notebook here. And that just launches in a web browser. And then we'll go down and find it, the one we were working with, Python Spatial. Okay, so this one should work. All right, so let's try to pull these in again, and we'll hit run there. Just executing it now, and then nothing, didn't give me any errors. So that means it should have found all the packages. All right, so here I'm reading in a shapefile from a folder on my local machine, and then I'm plotting it. So run there, and there we get our plot. And let's actually look at the data structure here. So here I'm just plotting the first few records. Hit run. And as we can see, basically this is another example of an object-based model. So you have a bunch of records that are like the attribute information, and then the geometric information is just simply stored as another record in the table. So this allows you to do table manipulations and make maps and do spatial analysis and spatial visualization in the open Python environment. Yeah, so I think, yeah, that's good. So now to finish up, let's look at an example in R. Okay, so here I'm in R, and I want to read in some spatial data. This is RStudio, which is an IDE for R. So I'm going to call in some libraries that allow for that. So we'll do library SF, and then I'm going to call in library tmap. So let's run those. Okay, cool. Oh, I didn't run the first one here. Run. Cool. So now we have access to SF and tmap. And you can see when I load it into SF, it links the Geos, GDAL, and Proj. Again, those are used in the background for dealing with projections and data types and whatnot. Here is the web page for GeoPandas. Sorry, not Geo. That was GeoPandas we already looked at. Here's the one for simple features in R, which again allows you to work with spatial data in R. There's a couple other methods too, like using SP. We're not going to look at that. Okay, so let's read in a data layer. So let's do st read, and then we got to give it a path to a data layer. I'm just going to go into one of these that we made. We'll just use this the states layer. Paste. And then let's swap over the slashes, and then underscore states underscore shape dot shape. And let's see if it finds that. Okay, and down here in the console, you can see that it said it found 49 features with 51 fields, and that it's a multi-polygon data type, and it's also got the projection information there. If you want to see it, you could do oh, actually I didn't set it to a variable, so we'll call it states. Rerun that. Okay, so now if we look in our environments, I have a bunch of other stuff loaded in here. But it should be listed there. There it is. So if we open up the table, again, we can see that this is a object-based type data structure. We have all your attribute information, and out here on the back end, you should have your geometry information somewhere. Let me go back to this real quick. On this again. So I'm just going to do a states, or we'll just do head of states. and that should plot the first set of records. There we go. And then there's the geometry column, and then all the other attributes. So again, object-based data structure. And lastly, let's try to map it. So we'll do tm shape, and we want to do states. And then we'll string onto that a tm polygons. And we'll do a fill. I believe it's fill. It might be collar. We'll see if it works. We'll fill it. I'm just... we'll just do something. We'll just do the population. So fill with pop 2000. So this is the population in 2000. Let's see if this works. Oh, it's really tiny down here. It didn't fill it. So let's see. It might be collar then. Let's try that instead. Call maybe? I don't know what the argument is. There we go, it's collar. So there we have all of our states drawn in, and we symbolize them based on the total population. Okay, so that's it. So this is an introduction to different types of data models for vector data. So working with open data models and also reading it in like open data science environments. So things like Python and R.